All right, we are talking confidence intervals. Welcome to chapter 10. This is a warning that says you need randomness, because if your sample is biased and it's either overestimating or underestimating your mean, then your interval is going to be in the wrong place. And any level of confidence that we try to apply to it is going to be trash. Your sample belongs in the trash if you didn't do it randomly. Okay, so we're starting out with this example, and we're going to sort of talk through this. So a school is trying to estimate the average IQ of its students. Let's say there's like 5,000 students. IQ tests are expensive, so they can't afford to do a census, so they take a simple random sample. Check, nice, of 50 students. And the sample mean came out to 112. So what can we say about the mean of the entire population of students? Well, since this is a simple random sample of 50, it should be representative of the population. And so we don't want to say that it's exactly 112, but we can say it's close to 112. The mean of the entire population. So mu is close to 112. Okay? But how close? How close? Well, we want to go some window away from it, but there's a specificity that we need. So let's look at the standard deviation of IQ scores. So this is actual real life. Standard deviation of all IQ scores is 15, okay? What will be the standard deviation of sample means if we take all possible samples of size 50? So we're talking about the sigma of x bars would be the sigma divided by the square root of n, like we saw in the last unit. And so we see that the standard deviation of all IQ samples of size 50 of IQ scores should be 2.1. Okay, so I have a sample of 50 of IQ scores, so the standard deviation should be approximately 2.1. How far above and below the true mean would we have to go in this sampling distribution to capture 95% of all sample means? Well, we know that the middle 95 is 2 standard deviations, plus or minus 2 standard deviations. So plus or minus 2 of these, okay? So that's where we're going to look to the left and right. So there's this unknown mu, and if we go plus 2 of those standard deviations, 2 times 4.2, and minus 2 times 4.2, we get this range of numbers that where 95% of all samples will be in here. So many x bars, 95% of them will be somewhere in here, and 5% of the time they'll be somewhere out here, okay? But 95% of my x bars are all in here, right? So most of the time, we're 95% confident. We have an x bar. We don't actually know where it is in the sampling distribution, but we know we're 95% confident that our x bar is in here, okay? And so since there's a 95% chance that we are within 2 standard deviations of mu, there's a 95% chance that mu is within 2 standard deviations of us, our little x bar, okay? So what we're talking about is this sort of picture here. So if this was my x bar, notice I capture this mu right here. Here, I can make a vertical line for us, right at mu, okay? And if I go 2 standard deviations below my x bar and 2 standard deviations above my x bar, I capture mu. It's only when I get out here past this line now, when I go 2 standard deviations, because I'm more than 2 standard deviations below, looking 2 standard deviations to the right is not far enough to capture it, okay? So since I'm 95% confident that my blue dot is somewhere in here, my x bar is somewhere in here, all of these, whenever my x bar is in here, which happens 95% of all samples, my interval going 2 standard deviations to the left and 2 standard deviations to the right will capture mu. And this one captures mu. And this one captures mu. This one captures mu, captures mu, captures mu, captures mu, mu, mu. These ones don't. So there's a 95% of all samples are in here. And so 95% of the time, we're 95% confident that our sample captures mu, although there's a chance that our sample does not. Okay? So We say we are 95% confident that the interval from here to here captures the true mean IQ scores for all students in the school. Okay, because that's the 112 minus 4.2 and 112 minus plus 4.2. There's only two possibilities. Our interval contains the true mean, or our sample was one of the 5% that is not within 2 standard deviations, and we didn't capture it. So we are 95% confident that we're one of these intervals. There's a 5% chance of that. Okay? But we talk about it as a confidence interval, and we say we are 95% confident. Okay? All right. So there's two things we talk about, the confidence interval itself and the confidence level. Okay? The confidence interval is the range of numbers. So like from A to B, from A to B, from A to B, from A to B, from A to B. All right? And we say we are whatever percent, the confidence level percent, C% confident that we have captured the population parameter. The confidence level is the long run probability. If this is 95%, then in the long run, 95% of our intervals will capture the parameter. So capture, 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 miss, capture, 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 capture. All the rest capture. Okay? And so 95% of the time it will capture if we are at a 95% confidence level. A confidence interval is the range of numbers from A to B. We usually write it in a parenthesis, like it almost looks like a coordinate, okay? But we write A comma B. We are 95% confident that the true parameter is between A and B, because in the long run, 95% of all intervals will capture. So the confidence level is a long run probability. The confidence interval is the range of numbers. All right? So we'll talk a lot more about these, and we'll see you. Good luck.